So our next speaker is Abigail Calzada-Diaz from Birkbeck College, who's going to talk about constraining source localities of lunar meteorites using remote sensing datasets. I'll wave at you when you've got 5 minutes.
I guess it's this one. Good afternoon, everybody. Well, as the title is saying, I'm a PhD student at Birkbeck College. And what my work is about is trying to figure out from which areas from the moon the different meteorites came from. That is, we recently published a paper. So recently, that was this month. So it's like really hot news. Why we want to know from where the meteorites came from. Yeah, we know that they are from the moon, but from where in the moon, it's important. It's important because we need to know what is the geological context of that samples. First what we want to do is to place the analytical results of some meteorites into the geological context. For what? Well, because all the samples that we have from the moon, they came from Apollo and Lunar missions, and they are from a really restricted area. So there are many other samples that they are different, or they came from other parts, and that they can give us information about the origin and the evolution of the moon. And also they can reveal new aspects of the moon that they are unknown until now. So here is in an image the Apollo and Lunar samples. As we can see, they are all just from, doesn't work anymore. So we can see that they are from a very restricted area. So we have practically no clue what's going on in the other part of the moon. That is what my work is about. Is like from where that part the lunar meteorites came from. So there are different types of lunar meteorites. To keep it simple, I don't want to get too much into geochemistry or to different type of rocks. We just classify broadly the lunar meteorites in these different types. What are impact melt breccias that are meteorites or rocks that they came from different type of rocks and they melt together because an impact event. There are pristine basalts. The pristine basalts are especially the rocks that came from the dark areas of the moon, from the mare areas. And we have regolith breccias. The regolith breccias are the ones that we are more interested about. They are the type of material that covers the surface, and they can be feldspathic, that means from the bright areas of the moon, from the highlands. They can be basaltic, that is from the mare areas, or they can be mixed, that is different type of material there. So the first part of this project was to create a database with the composition of the meteorites that we have until now, based in previous work. And we calculate the analytical standard deviation of the average measurements. And in the other part, we have remote sensing datasets. The remote sensing instrument allows us to know what is the different type of materials and composition of the moon. So for our work, we use lunar prospector, gamma ray spectrometer, and we choose three different. That's really bad. We use 3 different components. One is the iron, that in the top. That this allows us to distinguish between the mare or this basalt type material and the highland material of the rest of the moon. Then we have the thorium, that as we can see there is a hot spot of red. That is an area of the moon that have a high composition in thorium, and it's called the creep terrain because it has high composition in potassium and phosphorus and rare earth elements. And then the titanium. The titanium allows us to distinguish between different type of basalts, because in the moon we have different type of basalts. We have one type of that basalt that have low titanium component, and then we have another type of basalt that has high titanium component. So we used the 2 degrees datasets because it's like a good combination between the resolution and the accuracy in the measurements. So what we did for that, in one side we have the remote sensing dataset that has some measurements, I have some instrument errors, and in other hand we have the sample composition that we have the measurements and we have the analytical standard deviation. So what we do is to create a software application that allows us to combine these 2 types of data and it creates well, a shapefile in ArcGIS. I'm not really sure if you know what that means. That means well, this is a software that allows of visualization of data in a map, basically. So this software application shows us is, where are the areas where these two datas well, match. So first we have to check if this was right, if this has sense, or maybe it's just crazy results. So we perform a validation. The only way that we can perform a validation is with samples that we know from where they came from. So we choose the Apollo and Lunar samples. We know exactly which area they came from, and we have a lot of data about their composition, so we start to do that. Well, the red arrow points the landing sites. So as we can see, in general, they match quite well, relatively. I mean, the Apollo 11, yeah, the arrow and the white cross, it indicates the landing site, and we see that we have some yellow points that are the places where match quite near. And also in the Apollo 12 example, it fits quite well. It's in the middle of the thing. Obviously, we have more areas with similar composition. It fits quite well. In Apollo 15, yeah, there are some matches right in the area of the landing sites, and the Apollo 16. So we don't have matches in the sand area. It's like that we have matches in the highlands, and Apollo 16 is an area with highland material was returned. But we continue with the trying, and we in the Apollo 17 also quite good matches. Luna 16 and Luna 24 quite good, but in the Luna 20 is suddenly something we are going on, and we have different type of matches. So we need to know why this doesn't work so well, why there are some difference, why we don't always have the sat place. So, well, in general, we can say that the validation was successful, but there are discrepancies, as I saw. Well, first, the discrepancies are related with the spatial resolution of the instrument. We have an instrument that gives us 2 degrees resolution, that is like about 60 kilometers long, but the samples are from a really reduced area. I mean, the samples usually are from a point, like a centimeter or meter scale. So there are that kind of heterogeneities because the remote sensing data set, they make the average of a large area. But also we have another issue, that is the thorium composition that was reported in some meteorites are much larger than the thorium composition reported by the Lunar Prospector dataset. So that's really weird, and we check that, and that's true. And in that case, I don't know if you noticed that I didn't show Apollo 14 place. I hope you did. We didn't have any results because there are not results to show. So from that, we start to do this with 85 meteorites, pointing the pair stones, meteorites that are related with other meteorites. We have really interesting results. Well, I must say that this is not the first time that have been done. This type of work have been done many times in different ways. But what we can say is that this is the first time that this work was made in a systematic way. I mean, 85 meteorites can sound a lot, but actually using this software that we create, we were able to do it in just a couple of hours or something like that. We just not did new meteorites. We also wanted to do meteorites that we studied previously to check if the results are similar or what are the difference. So for that, what we distinguished was between the basaltic meteorites, that are the meteorites, as I say, that came from the dark areas, from the Maria of the Moon, meteorites that are mixed with iron medium composition, and anorthostatic or feldspathic meteorites, that are meteorites that came from the highlands, the bright areas of the Moon. So from the basaltic, I'm just show few of them. I can show many, but I just show few of them that can results quite interesting. The lab, this one is just a basaltic meteorite. And we have, as you say, we have different type of results in different areas. So that makes us figure out what we can do to restrict the results to one area. It's like, well, if we include in that the ages of these different flows, lava flows, maybe we can figure out in which area it came from. So in general, we cannot have 100% sure if we are right or we are wrong, but unless we have quite sensible results. In the intermediate breccias, this one is a meteorite that it has a really high content in thorium. If you remember, the thorium, it was high content in thorium. It was characteristic of this. Really, I don't know what's going on. It was high characteristics of, I cannot show, of this area of the moon. And the good thing is like that meteorite also, we have an estimate age of about 4 billion years. And that has sense. That has sense the results that we have. That has sense with the type of meteorite, and that has sense with the age, because that indicates us that it came probably for the Imbrium basin ejecta. The Imbrium is there. This area there. And also we have other quite interesting results. These two are two meteorites that are paired. It was originated from the same event, and we were glad that we obtained practically the same results. Things like still we were not able to restrict too much, but it's quite interesting results anyway. These two meteorites, this one, the Calcalon Creek, it was quite controversial because there are some authors that think that they came from the South Pole Akin Basin. Why? Because it has a really weird composition. It's like a mix of everything. It's like a mix of anorthosites composition. There is a mix with, there are also a basaltic component, there are high thorium components, like a mix of everything. So that can be for two reasons. Because one reason can be that really it's a mix of everything. So probably they came from that area there, that area in the moon, in the center. Or it can be because it's a type of, it's like a type of rock with that composition by itself. That is not like a mix, it's just that type of composition. Then it will come from the South Pole Akin Basin. Also, we have the South Pole Akin Basin as a result. Actually, most of the results are quite far from there, and we still think that it's probably that they came from the near side of the moon. And in the second, the Kalahari, that is really, it's one of my favorites. There are two meteorites quite different, but they came together, and they are really sure that they came from the same impact event and the same area. Kalahari 008 is a feldspatic rock, and Kalahari 009 is a basaltic rock. And they came together, they know that they came together because they have some similar isotopic composition, but also because they came together and they were found in the same place. So it's really weird that two different meteorites fall in the same place on the Earth. So what is interesting is like the Kalahari 9, the basaltic, is the oldest basalt known from the moon. And it was interesting that we have results in areas that they suppose that there are cryptomare. This cryptomare is really, really old, ancient mare that was later covered by a ejecta of other impacts. So as we know that these rocks are together, we see that the Kalahari, the feldspatic that covers this basalt, it comes more from the Mendel-Rydberg area. We can figure out that probably these meteorites came from that area, from the Shikar-Mendel-Rydberg area, and it was a basaltic flow from a cryptomare covered by an orthositic material. So it was quite interesting results. And finally, the feldspatic meteorites. We have, in general, with the feldspatic meteorites, we see that we have all the data that we have are really, they don't say too much, except in the last case. In the other case, they are really similar, and they don't really specify where they came from. And actually, when I show you the remote sensing dataset, probably you realize that one differentiate different type of basalts, other differentiate anorthositic basalts, but nothing differentiate really the different type of anorthosites. For that, we were planning to use magnesium. The problem is like the data obtained from that instrument from magnesium, it was not really good, so we decided not using and just go on what we have. So we have really spare data, but still they tell us something. And in the last case, this one, NWA 4932, what we have is like, we have a really specific set of matches in Mare Australe. That's really interesting because this meteorite is a feldspathic meteorite. I mean, the composition is completely feldspathic from the highlands, but it has quite high content of iron. The iron is more the high content, intermediate content. Is not like the basalts that have much higher. And it's a type of meteorite that has never saw something similar in all the samples that we have for the Apollo and for the lunar mission. So it was interesting that most of the results that we have are related with the Mare Australe of other areas with cryptomare material. So despite that we have a successful validation, there are several things that we have to take into account using this approach. That is like, first is if we have measurements and what is the quality of that measurement. And also, well, the remote sensing instrument. The accuracy in the abundance, for example, in the magnesium type, we thought that was not high enough to use it, and also the spatial resolution of the instrument. If we were able to have data from remote sensing with better spatial resolution, probably it will be easier to figure out and to restrict much more our results. But this is just a project that is ongoing. So we have other plans to improve this. It's like, first, integrate the chronology data when possible. For example, knowing the ages of the basaltic flows will help to really discriminate different lava flows. And yeah. Also, we would like to explore other data sets to find if we have better measurements and also better spatial resolution, and also because if we have other type of data set, we can integrate maybe all together and we can restrict much more the results. And finally, make the data set and the software that we use available to the community. And also these days what we are doing is carry on our own sample analysis. So we are analyzing two meteorite samples, Miller range 090036 and 090070. There are two feldspathic regolith breccia, and we would like to then use to try to figure out from where it came from. So finally, well, we made possible to do a systematic approach to match meteorite with possible launch regions. We perform a successful validation despite there's some small constraints. We use this approach, we apply it to 85 meteorites, soon will be more. We would like to integrate with other compositional and mineralogical remote sensing dataset to have better results and constrain much more the place than the geological context. And finally, we would like to integrate the chronology data when it's possible, like especially in the basalts. And that was all. Thank you.
We have time for a few questions. There's Kathy just in front of you.
So, oh, sorry, I forgot about that. Does this technique have the potential to apply to, say, Mars in the future?
We were thinking about that, but we should check, because in Mars the moon has no atmosphere. There are more simple surface processes, but Mars is much more complex. There are other things to take into account, like winds and different. So I'm not really sure. We can think about that, but we are not really sure if we'll be able to apply to that one.
I'm not quite sure how you select your lunar meteorites in the first place. I mean, how do you know they don't come from somewhere like Vesta, for example, which also has basalty things?
Well, there are several, ways to distinguish that they came really from the moon. One is the composition of the basalts of the meteorites. They low half of volatiles. They don't have almost volatile. Well, they don't have almost. No, they are practically lack of volatiles. So they are really certain that they came from. And many of them have most of them have really similarities with other samples from Apollo and Lunar missions that we know certainly that they came from the moon. So yeah, there's no doubt about that.
Okay, with no other questions, let's thank our speaker again.
Thank you.